Hello everyone. Today we discuss some extension of the limit concept. That is, in chapter 3, we talk about the limit of a sequence. In chapter 4, we extend that notion to the limit of a function. A sequence is just a special function. Now we're gonna go a step further by extending the notion of the limit itself. The first extension is about one-sided limits. Originally, we had x approaching c from both directions. One-sided limit is about the consideration of x approaching c in only one direction. So here is the definition. The limit when x approaching c from the right of the function f equal to some number L. This equal a right hand limit. Even on it, given any epsilon bigger than 0, there exists delta depending on epsilon bigger than 0, such that for 0 smaller than x minus c smaller than delta, then fx minus L here in absolute value is smaller than epsilon. So this is a very similar definition to the definition of the limit of function. The only difference here is that here we only consider 0 smaller than x minus c smaller than delta. That is, in this case, we have x is bigger than c, and x approaching c from the right. That's why I call a right hand limit. Similarly, we have a definition for a left hand limit when x approaching c from the left. So the limit of the function f when x approaching c from the left equal to L, even only if given any delta greater than 0, they exist. Given any epsilon greater than 0, they exist delta depending on epsilon greater than 0, such that for 0 smaller than c minus x smaller than delta, then fx minus L in absolute value is smaller than epsilon. So in this case, we only consider x smaller than c and x approaching c from the left. That's why it's called a left-hand limit. Here is an example. Let f of x be the side function of x. That is equal to 1 if x here bigger than 0, equal to 0 if x equal to 0, and equal to minus 1 if x smaller than 0. We can easily show that the limit of this function in general doesn't exist. However, when we consider one-sided limits, then certain one-sided limits of this function exist. For example, if we consider x approaching 0 from the right, then x here is always greater than 0. That's why the sign of x is always equal to 1. So the one-sided limit here equal to the limit of 1 when x approaching 0 from the right, and this is equal to 1. Similarly, if we consider x approaching 0 from the left, then x is always smaller than 0. That's why the value of the function is equal to -1. That's why the limit here equal to -1. And here some observation. The general limit of the function f of x equal to L if and only if one-sided limits of this function agree and also equal to L. And we can see exactly why the general limit for the psi function here doesn't exist. The explanation is that one-sided limits of this function do not agree with each other. When x approaching 0 from the right, the function approaching value 1. When x approaching 0 from the left, the function approaching value -1. The second observation is that there are modified versions of theorems established for the limit concept in section 4.1 and 4.2 applicable to one-sided limit. We skip them and you can read more about these statements in the textbook. Now, the next extension of the limit concept is about the infinite limits. So this is corresponding to properly divergent sequence. That we discussed at the end of the previous chapter. So here is the definition. The limit of the function f of x equal to plus infinity if for every alpha real number, thinking about a very big real number alpha, there exists delta depending on alpha greater than 0, such that for 0 smaller than the absolute value of x minus c smaller than delta, then fx here gonna be bigger than alpha. So in this case, we know the function doesn't converge to a number, but we also know the direction it diverges to. And a similar definition is that the limit when x approaching c of fx equal to minus infinity if and only if the limit of minus of the function f equal to plus infinity. We can define the one-sided limit for a function to be plus minus infinity in a similar manner. And this is definition 4.3.h in the textbook. Now let me give you some example to really illustrate the spirit of this definition. We want to show that the limit of the function 1 over x squared when x approaching 0 is equal to plus infinity. Remember, plus infinity is not a number. So in order to solve this problem, we had to apply the definition. Let alpha be a real number, thinking of a very big real number. And we can assume that alpha bigger than 0. We want to choose delta depending on alpha, but at the moment we don't know a good choice of delta yet. So let's do some estimate, and hopefully the estimate gonna lead us to the appropriate choice of delta. So we want to show that for x within delta neighborhood of 0, then the function is bigger than alpha. That is, for 0 smaller than the absolute value of x minus 0 smaller than delta, then 1 over x squared, which is equal to 1 over the absolute value of x squared. And because x here is smaller than delta, so 1 over x squared is greater than 1 over delta squared. That is, we want to choose delta such that 1 over delta squared is greater than or equal to alpha. So this estimate certainly leads us to the choice of alpha equal to 1 over square root of delta to be 1 over square root of alpha. So 1 over delta square gonna be equal to 1 over alpha, which equal to alpha. Then we have that the function 1 over x squared going to be greater than 1 over delta square, which is equal to alpha. So the choice, the correct choice, the appropriate choice of delta here is delta equal to 1 over square root of alpha. Now then the definition is verified, so we can conclude that the limit of the function when x approaching 0 is equal to plus infinity. So the step right here, this step here is just the thinking process. Another example is a function gx equal 1 over x. Applying very similar arguments, we show that the one-sided limit of this function when x approaching 0 from the right equal to infinity plus infinity, but the one-sided limit of this function when x approaching 0 from the left is equal to minus infinity. Now, another extension of the limit is about limits of infinity. Here is the definition. Limit of the function f when x approaching infinity equal to L, even only given delta bigger than 0, there exists k depending on s, given epsilon bigger than 0, there exists k depending on epsilon, such that for every x bigger than k, we have fx minus L is smaller than epsilon. An equivalent statement is that for every sequence xn such that the limit of xn equal to plus infinity, then the limit of fxn f of xn equal to L. So this is the sequential criterion. Here an example, the function gx equal 1 over x. We want to show that the limit when x approaching infinity of this function is equal to 0. Here is the proof. Let epsilon bigger than 0. We consider fx minus L, and L here in this case just equal to 0. So this is equal to 1 over x minus L, which is 1 over x. And we consider this number in absolute value. Now let k be 1 over epsilon. Then for x bigger than k, we have fx minus L is going to be equal to 1 over x, which is smaller than 1 over k, which is equal to 1 divided by 1 over epsilon, which equals epsilon. So here, I skip the thinking process. You would imagine that if we follow the thinking process, we need to estimate the function first, and that estimate leads to the choice of k depending on epsilon. But here I skip that thinking process and immediately give the appropriate choice of k depending on epsilon equal to 1 over epsilon. And then the estimate works. And the definition is verified, and the limit of 1 over x when x approaching infinity equal to 0. Now, the last extension of the limit concept we discussed today is about the infinite limit of infinity. So everything is going to infinity. So here is the definition. The limit of the function f of x equal to infinity when x approaching infinity, even only given a number alpha, very big number alpha in the set of real numbers, there exists k depending on alpha such that for any x greater than k, fx is bigger than alpha. Then we have a ratio test for this notion of limit. Assume that the function gx is positive, and the limit when x approaching infinity of the ratio fx divided by gx is equal to L, different from 0. Then we have the following statements. First, if L is bigger than 0, then the limit of f equal to infinity, even only the limit of the function g equal to plus infinity. Similarly, if L is smaller than 0, then the limit of the function f is equal to minus infinity, if and only the limit of g here equal plus infinity. So here, in this situation, where two functions proportional to each other, but this proportion, this ratio, has a sign, it might be positive or negative. That's why when it is positive, both functions approaching infinity plus infinity together. If the sign negative, then one function is approaching plus infinity while the other function approaching minus infinity. And here we have an example of how to apply that theorem to compute the limit of x to the n when x approaching infinity. And we show that the limit is equal to infinity. The argument here again is based on the definition and some comparison argument. Now, in summary, I would like to give a very overall description of what we discussed today. The limit concept is described at two levels. The level one is x approaching some number c. The level 2 is f of x approaching some number l. So in order to extend this notion, we can get several extensions depending on what level we consider the extension. So we can extend the concept at level 1 by different methods. Instead of x approaching c, we can let x approaching c plus. That leads to one-sided limit or c minus. Or another way, another extension is to let x approaching infinity. That leads to the notion of limit at infinity. At level 2, instead of fx approaching L, we can let fx approaching infinity. That's gonna lead to the notion of infinite limit. So these are the 1, 3, and 2 extensions we discussed earlier. Combining 2 and 3 leads to the last extension that we discussed, number 4 here. And 4 here is about the infinite limit at infinity. And that's it for today.